section we had. So let's start from there. So I'm sure some of you might have looked at it again and it's clear to you, but so that it will be in the recording and it can be very clear to those that maybe might have internet connection. So we start with 2.5 again. The question said we should look for the tensor that transforms the basis vectors as follows. So we are looking for a tensor T that transforms E1 to become E1 plus 2E2 plus 3E3. And that same tensor transforms E2 to become minus 5E1 plus 4E2. And that same tensor transforms TE3 to be 3E1 minus E2 minus E3. So, and from the last session, we saw that when we are looking for that tensor, what are we actually looking for? Are the components of the tensor. So we are looking for, what we're actually looking for is T11, T12, T13, T21, T22, T23, T31, T32, T33. Of course, we know that in index notation, a tensor T can be written as Tij, Ei, Ej. So what we have in the matrix form is actually the Tij. This part is what I've written fully out here, which is the scalar component of that tensor. So the first thing that we did was, we know that if the tensor operates on V, what we'll have in component form will be Tij, Ei, Ej, which is the T, operating on, of course, we cannot use I and J again. If not, we will break the rules of index notation. We have to use some other subscript. So I'm going to use alpha is equal to V alpha E alpha. So this TV in index notation in component form is what I've written out. And we know that this gives us, we bring out the scalars, which is Tij, V alpha. My apologies, this shouldn't have a bar because that's the scalar component of that vector. V alpha, then we'll have Ei, Ej. So I'm filling in some of the gaps that are not in the notes. Of course, this was not shown, okay? And this gives us Tij, V alpha, Ei, Ej dot E alpha. And this is the importance of chapter 1. If you did not understand what is going on in chapter 1, you will not understand what I just did. And that's why chapter 1 comes before chapters 2. And this gives us Tij, V alpha, Ei, chronicle delta J alpha. The chronicle delta also acts as a substitution symbol. We will see that we have alpha on the chronicle delta and we have alpha on the V. So we can substitute that symbol and take off the chronicle delta. And this gives us Tij, Vj, Ei. Okay, so that was the first thing that we did. And if you look at the notes, if you open to your 2.5a, you would see that you have applying TV is equal to Tij, Vj, Ei. So what I just did was to clarify how TV became Tij, Vj, Ei. Now, the next thing that we did in the last tutorial session was to now write out Tij, Vj, Ei fully, to write it out fully. So that was the next thing that we did. Can I take off what is on the board, or should I pause a bit? In case I'm too fast, please let me know. I'm just reviewing what we did last. Can I go ahead and take off what is here so that we have the space to write Tij, Vj, Ei fully? So I'm taking this off so that we have the space to write out our Tij, Vj, Ei fully. So next, we want to write this out fully. Of course, you will see that I is repeated, J is repeated, so you have some summation going on there. I and J going from 1 to 3, we write that fully. It will be T11 V1 plus T12 V2 plus T13 V3 E1 plus T21 V1 plus T22 V2 plus T23 V3 E2 plus T31 V1 plus T32 V2 plus T33 V3 E3. So we've written that out fully. But remember that if we look at that 2.58, the question, we are looking for a tensor T that transforms E1. Remember that what we wrote out was for T operating on V. So if we compare these two, we are saying we are looking for a tensor that transforms V when V equal to E1. So if V is equal to E1, what will be V? What is V? If V is E1, what is V? We know that when we are writing V in full form, in index notation or component form, is written as V1 E1 plus V2 E2 plus V3 E3. So for V to be equal to E1, it means that V1 must be equal to 1, V2 must be equal to 0, and V3 must be equal to 0. So if we are looking at the tensor that transforms E1, for the Tij, Vj, Ei, we have written in full form. For this first transformation, we are looking for the tensor T that transforms E1 to become E1 plus 2E2 plus 3E3. So if my V is supposed to be equal to E1, in what I've written now fully, it means that all my V1s will be 1, all my V2s will be 0, and all my V3s will be 0. That I will do to answer this first transformation. So this is the first one I'm looking for, where my V is equal to E1. Remember, for my V to be equal to E1, V1 must be 1, V2 0, V3 0. So when I apply that, I'll see that what I've written in full form would be T11 into 1 plus T12 into 0 plus T13 into 0, E1 plus T21 into 1 plus T22 to 0 plus T23 into 0, E2 plus T31 into 1 plus T32 to 0, T33 into 0. Please keep in mind that this is, we are answering the first one. And for the first one, V, instead of V, we have E1. And for us to have V equal to E1, V1 is 1, V2 is 0, V3 is 0. So when we apply that, we see that what we now get to be T11 E1 plus T21 E2 plus T31 E3. And that should be equal to E1 plus 2E2 plus 3E3. So comparing the left-hand side and the right-hand side, you will see that your T11 is 1, your T21 is 2, and your T31 is 3. So we've gotten 3 of the 9 components of the tensor. We've gotten 3 of them. We've gotten T11, T21 to T31. Is this clear? Should I pause again? If you have any questions, please post in the chat or you can raise your hands. Okay, Mojirade, I'm happy that this is clear. Can I get any other comments so that I know whether I should move on? Or okay, Mubarak, good. This shows that we actually went back to look at it. Fantastic. So for everybody, you know what will happen when our V is equal to E2. So the tensor that transforms TE2. In that case, for V equal to E2, your V1 will be 0, your V2 will be 1, your V3 will be 0, and substitute all that in your component form, that full component form, you would get T12, T22, and T32. You do that also for when V equal to E3. For that case, V1 will be 0, V2 will be 0, V3 will be 1. And for that, you will get T13, T23, and T33. And you will get your full 9 components in that, your tensor, the matrix. What I said now, is it clear? So that we can move on to another question. This is just to clarify what we're looking at. So if you look carefully, it means that you should get your tensor components. If you look at that 2.5 as 3 minus 5, 3, minus 1, 0, minus 1, minus 1, 4, minus 1. That will be your tensor components. So I'm just pausing to see if there are questions or comments. So let me take this off. So I want to look at 2.6. 2.6 is not really complex, but there is something, there's a pattern recognition I want you to see there that you will need for some other questions. So let's look at 2.6. So 2.6 says, and before I go on, for the B and C parts, you can actually use Mathematica. So for you to get the reverse transformation, it means that that tensor component you have, if you can put it in Mathematica and do the inverse of that tensor, Mathematica will just give you the component straight on. So if you use the built-in function, the inverse of a matrix, and put in this matrix in Mathematica, it will actually give you 4/33, 7/33, 5/33, and all those components there. Instead of you working it out, that will take you a long time. And you can now proceed to the to the other parts of the workings. Okay, so let me go to 2.6. Given vectors vectors u and v, find the tensor that transforms any vector A to u into A dot v. Of course, we all know that if we have u, because A dot v, the output of that is a scalar and it is commutative, we can rewrite that as u to v dot A. And of course, from your chapters 1, you know that this result actually comes from u dyad product with v A. So what I just did now is from chapters 1. So we will see that the tensor we seek is simply the dyad created by the vectors u and v. The question said, find the tensor that transforms any vector A to u into A dot v. So you will see that this is the tensor that transforms vector A into u into A dot v. Very simple. The second part of that question, given vectors u, v, w, and x, show that the dyad product, which is actually the one I actually want to deal with, so show that this dyad product is equal to so if we look at this carefully, this is what we want to prove. The first thing is that you have to make this dyad product operates on a vector to actually check that equality. So let that dyad product operate on the vector y. So what we want to check is that when this dyad product operates on y, it will give us, is the same as this. So if your output on the left-hand side and your output on the left-hand side gives you the same results, then you know that these two are equal. We know that these two are equal. So let's deal with the left-hand side first of all. You know that I can rewrite this as u, the output of v, w, x dot y. We know that from chapters 1. And of course, you can also rewrite this as u into v dot w, x dot y. Also comes from what we know. When the dyad is operating on a vector, you get that. Okay? So you can see that this two we get from the left-hand side. Now let's look at the right-hand side. Look at the right-hand side carefully. You would see that what we have here for the right-hand side, you can write this as, because v dot w is a scalar, we can write this as u just changing the position of where that vector is, because the dyad operates on the vector. V dot w is a scalar. And we know that this you can also write as u so we can see that the left-hand side and the right-hand side, they are the same. But what is the important thing that we want to learn from here? The important thing is that when we have dyad products, series of dyad products, there's a pattern recognition in how you can rewrite it. So if you have dyad A, compose it with C, compose it with E, just a general formula. This is the same as you taking the first vector in the dyad, first dyad, and the last vector in the last dyad, compose it as a dyad. Then the inner vectors, you will do a dot product. So when you have this dyad composition, series of dyad composition, it can be rewritten as this. And if you check the example we just dealt with, U dyad product V, W dyad product X, you will see that your results is when it acted on Y, when we see it on Y, the result that you get is the same as saying you are composing U and X, and you do V dot W as a dot product. So U dyad product V, W dyad product X. Look at this here. Look at what it gives you here. So it's the same as taking your U and taking your X, compose it as a dyad, then the inner vectors in the series of the dyads will now become a dot product. And you see that you have the same answer. Can you see what I'm showing you as the patterns for when you have series of dyad products being composed together as a product? Can we see it clearly? So that's just what we wanted to do. Now 2.7 is in the previous recorded video, so that we don't need to repeat it. If you listen to that video, you will see that there are a couple of exercises I did there also. So 2.7 is already there, 2.8, 2.9, but I want to go to 2.10 because what we get from there will also help us in some other questions. The thing about these solved problems is that when you get the pattern and understand the previous solutions, you will see that you will need them when you are moving to other questions. Okay, so let's go to 2.10. Show that for any invertible tensor S and any vector U, the vector cross of that tensor SU vector cross is equal to the cofactor of S composed with U cross, that vector cross, composed with the inverse of S. So we are supposed to prove this. That's what 2.10 is asking us to do. Of course, we know that what we will get on the left-hand side is a tensor. What we get on the right-hand side is a tensor. The compositions of tensors gives you a tensor. The vector cross is a tensor. First thing that you need to note is that the cofactor can be written as the determinant of the tensor S, which is a scalar, multiplied by the inverse of S transpose. So we can actually rewrite what we've been asked to prove. So what we've been actually asked to prove is that this vector cross is equal to determinant of S inverse of S transpose which we can also rewrite as U cross. Of course, we know that the determinant of our S is a scalar. So we can write it as, if we compose both sides with the transpose of so what I'm doing is that I'm composing both sides with the transpose of S. So what I did on that side, I must do on this side. So what does that now give me? So that would give me, I forgot the determinant. I've not written the determinant. So let me write it. I missed that out. So let me rewrite that. So what I will have is U cross okay, determinant of S I've written those two out. And remember that when I'm composing both sides with this transpose, what I will actually get is that S transpose, these two, will give me identity. Am I correct? Am I correct? Are we still here? Are we following? Just let me know. Are you following what I'm doing? I'm just rewriting what is on the left-hand side and right-hand side. What I've done so far, do you understand what I've done? Okay, let me start again. This is what we are supposed to prove. We have another way of writing our cofactor. Okay, I can see the no. Don't worry. One person has said no. So one no is enough for me to know that I need to do this again. Now, what I've ticked, this step and this step, do you understand that? That the cofactor can be written as determinant of S, inverse of the transpose of S. Is it clear up to that point? Good. Now, instead of you having cofactor of S, replace that with determinant of S and the inverse of the transpose of S. So this step, this third step, this is question 1, this is 2, this is 3. Is step 3 clear? So instead of me having cofactor of S, I've substituted that cofactor with determinant S and inverse of S transpose. Okay, good. Now, what I'm trying to do now is I want to rewrite what is on my right-hand side in another form. I know that when I compose a transpose with the inverse of its transpose, I get an identity tensor. What am I trying to say? If I have S and compose it with S inverse, I have identity. So if I have S transpose and compose it with inverse of S transpose, I'll get the identity tensor. These that I've written here, is it clear? What I just put in the circle, is it clear? All I'm doing is just the tensor manipulation. Okay, I can see Modirade says it's clear. Good. So what I now did was that I now did that composition. But if I do it on the right-hand side, I must do it on the left-hand side. Okay. So what I did was that I composed S transpose. I introduced that S transpose on the right-hand side, composed it with the inverse of that transpose because I want to get an identity there. But whatever I do on the right-hand side, I must do on the left-hand side. And that was why I introduced it here. So this is step 4. Is step 4 clear? No, I've cancelled it. It was a typo error. Bolaji, I just saw it. It's inverse of S. So I've erased the second one there. Okay, fantastic. So we are all on the same page. So what do we now have? So the proof that we are asked to prove. Oh, okay, good, Mohammed. Your audio was off. So you could, yes, you could hear it on the recording. So what we want to prove actually, step 1 can be rewritten as this. So this is the proof. But remember again, look at step 2. Look at step 2. So you can apply that step 2 to my step 5. I can apply that step 2 to my step 5 and rewrite it as so all these manipulations I'm doing now, you can need it for another question. So that's why I'm showing the steps. So this will be the transpose of the cofactor. Look at step 2. Look at step 2. You will see that your cofactor is written as what we have there. Okay. So if I transpose that cofactor, I will get what I have in step 5. So I'm on step 6 now, and I need you to check that that is correct. So everyone, look at step 2, apply to step 5. Is step 6 correct? Is step 6 correct? Just waiting for you to confirm that. Is determinant of S composed with the inverse of S the same as the cofactor transposed? Fantastic. So step 6 is now what we are going to use for our proof. Because from step 1, what we did from step 1 to 6 is just to rewrite the question. And each of those steps will be useful for you in other questions so that you can do your tensor manipulation and following the rules. All that I did was I just followed the rules, that's all. And I wrote the question in another form. So this is what we are going to use for our proof, step 6. Step 6 is what I'm going to use for my proof. So can I take this off so that I can write this step 6 and we can now do the proof step by step? Can I take off what is on the board so that we have the space? Just waiting for you to respond. If I can take it off. Just to be sure that everyone can hear me. Or are you writing? Okay. Okay, Godwin says I can take it off. Look at step 2, Bolaji. Look at step 2, Bolaji. Just transpose that cofactor. Remember that the determinant is a scalar. So you are not going to transpose that. Just transpose step 2. If you transpose step 2, you will see that what you will get is determinant of S inverse of S. Bolaji, I hope you can see. So all you just need is transpose step 2. You will get the right-hand side on step 6. So I'm going to move on right now. So all you just need to do is write. No, I cannot respond to your complaint again because we've moved on I'm thinking that by the time you listen to the recording, because I can't even remember, because it's from another question. So your audio was off when I was calling you to speak. So I don't know, I can't even remember what the complaint is, Mohammed. So Mohammed, you can post it again. Akyode, you are writing. Okay, so everybody, let's just pause for one moment. And for the rest of us, you can look at 2.10, the other steps in the notes before I start. Okay, well cleared. Okay, fantastic. So I'm taking this off. So what we are proving now, we have rewritten our question as S transpose this vector cross. We want to prove that is equal to U cross transpose of the cofactor. So that is simply what we want to prove. And what can we see here? There are I think 4 major things I want to see here. On the left-hand side, we have S transpose. We have SU cross. On the right-hand side, we have, okay, Fisayo is putting in some explanation. We have U cross, and we have transpose of. So we have to write each of these in component form, compose these two, and compare what we get by writing this in component form and composing it. So if the left-hand side gives us what is on the right-hand side, then it means that it is actually equal. Now, the reason why we are showing the steps is the steps, like I said earlier, will be useful for other questions. Now, how do you write S transpose? So let's assume in component form, my S is S alpha beta. I'm going to write it exactly the way I worked it out in my notes so that you can just follow. Okay, I think Fisayo Bolaji got it. So I'm going to use the same thing I used in my notes step by step so that there won't be any confusion. And the indices that I'll be using might be different from what is in the notes, but all you just need to look at is the pattern. That's all. It's not compulsory you use the same indices. In fact, in the self-test, you might not even see the same indices. It's not comprised exactly the same. If I write S equals to SMN, EM, diet product with EN, it's the same as saying SIJ, EI, EJ. So you can use any index. So I'm not going to use the same thing that we used in the notes. So let me use what I used. I tried as much as possible to kind of follow what is in the notes, but if you see that I deviated, just follow me and look at the pattern. Let me first of all write U cross. U cross, of course, everybody in this class should know how to write the cross now. My alternating symbol, I, alpha, L. Those are the indices I want to use. And for the U cross, you know that the middle index is what will be on my U, my component of U, and the others will form my dyad. That's my U cross. Now I'm going to write SU cross. I won't use the same index, but the only thing is that I'll keep the middle one. I'll keep the middle one because, you know, we are looking at the left-hand side and the right-hand side, okay? So SU cross, I'm going to write that alternating symbol L alpha K. I can use that because U cross and SU cross are not on the same side, okay? So I won't be repeating in indices on either of the side. So I'm going to write it as that. SU alpha EL MEG. What I've written so far, is it clear? So I don't go too far before I get a no. What I've just written is U cross and SU cross. Is it clear? Okay, Mujirade, good. Waiting for more responses. Oh, okay. Mubarak, why is it not clear? The only reason that it won't be clear is that you didn't read through vector cross. Like I said, most of these things, because the tensor algebra is a language, is for you to recognize pattern. This is the way a vector cross is written. The only difference that you will see is that the indices used are different. The vector cross is written as the alternating symbol with the three indices, the component of the vector itself, and the dyad. And the proof is in your notes. But what I just did now is to write for how it looks like. So if I have I alpha L, the middle index on that alternating symbol is going to be the component of your vector, U. The other two indices, the first and the last, will form your dyad on the basis vectors. Mubarak, can you see that pattern now? And I just applied the same thing to the SU cross. So there's a way that a vector cross is written in component form. So you just need to go. So you need to go back to your notes and check that. We only need this form here. All right, so we've written the two vector crosses, but we need to actually write this properly because this is not in full component form. Remember, you look at it, my U still has a bar. The reason is because S operating on U will give you a vector. So how am I going to write this now in component form? So I'm taking SU out now. SU alpha. This is what I want to deal with now, not with the whole thing yet. Then I'll put whatever I get back into that, that expression. Okay. So how do I write this now? To write this, I'm going to show you the pattern. The pattern is the alpha will be on the S, and you will use a repeated index for your J, for your U. So if you have your component alpha on this SU, if you want to write that SU in the component of SU, it's going to be S alpha J UJ, or S alpha I UI, or S alpha M UM. The only thing is that the alpha must be the first index on your tensor. Let me show you another example. If I have TVJ and I want to write it in component form, this will be TJM VM. So I just need you to recognize that pattern. So the component of TV will be written this way. The component J must be the first index on your tensor. And the proof of how this is written also, you need to go back to your notes. But majorly for tensor algebra is mostly pattern recognition. Must be able to recognize the patterns of how a particular form is written in another form. One more example before I move on so that you can recognize the pattern. If I have a tensor S operating on A, and I'm looking for the ith component, this in component form I'll write as S I J A J. So the I will be the first index on the tensor. Please, is what I've done clear? Because I need to now rewrite, put that back in the expression we are dealing with. Is it clear? Good. So just remember that pattern. Fantastic. Good, good, good. So let me clean this. So I'm going to write that component form back inside that So my SU cross, I can now write as EL alpha K, S alpha, alpha J, UJ, EL, EK. Now, the next thing I want to write is my cofactor of S, which also has a pattern, and is in the notes. So everybody just watch. When you are writing the cofactor has two alternating symbols, and it starts with alpha. All the proofs are in the notes, but the question is not asking us for proof. Your self-test is just to ensure that you know how to write your cofactor in component form, your component form back to the number tensor form and all that. So your cofactor starts with alpha, has two alternating symbols, has two tensors, and has a dyad. What is missing from what I've written now are the indices, because the indices is what shows you the pattern. So for example, if I write JAB for the first alternating symbol, of course, I will use another index for the second alternating symbol. I'm just choosing that arbitrarily. You can use anything, MNP, whatever it is you want to use. So remember, your cofactor starts with alpha. It has two alternating symbols, two of the tensors, and the dyad. So the pattern is the first index on the first alternating symbol and the first index on the second alternating symbol is what goes on your dyad. The second index in your second alternating symbol will be the first index on your first tensor S, and the first index on the second alternating symbol will be the first index on your the first two indices, the second and the third index on your alternating symbol goes to your first tensor, and the second and the third indices on your second alternating symbol goes on the second. So if you watch my steps now, you can write, if you have any question that has you saying the cofactor of a tensor in component form is written as, all you just need to check is the pattern on the indices, the fact that it starts with alpha, it has two alternating symbols, two of the tensors, and the first index on the two alternating symbols make up your dyad, and the rest follows. Do you understand how this pattern works for you to be able to write your cofactor? I think I even made a mistake here, and I'm going to apologize for confusing you. The first thing I did was correct. So please, my apologies. I'm looking at my notes, but I mistakenly took one part of the notes for the other. So the first thing that I did before was correct. Second index, third index. And the reason why I'm doing that, I don't want to go through the proof. So Godwin asked me to come again. So I'm going to clean off this cofactor and I'm going to start again. So for those that got it and I made a mistake and now got you confused, let me do it again. I want to write the component form of the cofactor. The cofactor has half, two alternating symbols, tensor appearing twice, and the dyad. That's the first thing. The only thing missing are the indices. So you choose your indices. You can choose anything and put them first on the alternating symbol. So what I chose was JAB as my indices on the first alternating symbol and beta CD as my indices on the second alternating symbol. Now, the first index on the first alternating symbol and the first index on the second alternating symbol is what goes to your diode. The second index on the second alternating symbol and the second index on the second alternating symbol goes to your first S. The third index on the first alternating symbol and the third index on your second alternating symbol goes to your second S. And this is how you write the cofactor of a tensor in component form. Is it clear now? You know, I cleaned something. I know Mojirade, Mubarak, Fusayo, they were clear, but I corrected the mistake now just to be sure that everybody, we are all on the same page. But if you look at our question, what we actually need is the transpose. All you need to do when you are transposing your tensor is to look at the diode. You don't have any business with the scalars. Half is a scalar. Your two alternating symbols are scalars. Your two component form of S are scalars. So when you are transposing your cofactor, all you just need to do is swap your diode. Swap the basis vector on the diode. So the transpose of that is half alternating symbol JAB, alternating symbol beta CD, SAC. So all the scalars still the same. And I just swap my basis vectors. That's all. Once you swap the diode, you have transposed. Is the transpose of the cofactor clear? The only thing left now is for me to write S transpose. If you look at the question, we are just breaking down all the elements there. If you look at the question, we have S transpose, we have SU cross, we have U cross, we have SC transpose. We have written the U cross, first step. We have written SU cross, second step. And we have written your SC transpose. The only thing left now is to write S transpose. For my S transpose, which is the fourth thing I'm writing, let me squash it into this space so that everything can be seen together. I'm going to write my S in component form as SI beta EI E beta. So my S transpose, like I told you, just swap the diode. It's going to be SI beta E beta EI. Another way that you could write your S transpose is to leave the diode and swap the index on your S. So another way of writing your S transpose is S beta I EI E beta. So any of these two is correct. But you cannot swap both at the same time. If you look at the first transpose, I only swapped the diode. I left the indices on the S. If you look at the second form of writing the transpose, I only swapped the indices of S and left the diode. You cannot swap both at the same time. So we have our S transpose, SU cross, U cross, SC transpose. So I'm going to compose these two on the left-hand side. Look at what my result is. Compose these two on the right-hand side. Look at what my result is. Compare it and see that is the same. Up to this point, are we good? Are we good? Are we good up to this point? Okay. Mojirade, I see you. Just waiting to get 2 more responses. Okay, Mubarak, I see you. Any other person wants to jump into the chat? Godwin, Akinola, Fisayo, Bolaji. Are we good? We've written the component forms of all the tensors we want to work with. Okay, fantastic. Okay, so I'm going to take off what is here. Okay, good. So now let's start with the is it the right hand side now or the left hand side? Okay, let me start with the right hand side. So I'm going to write U cross cofactor transpose in component form. So it's just putting all the component forms together. So for my U cross, I had alternating symbol I alpha L, U alpha, EI, EL. Okay, that's for my U cross. And for my cofactor of S transpose, I had half alternating symbol JAB, beta CD, SAC, SBD, E beta, because you know it's a transpose, so I've swapped the basis vector, E beta EJ. So I'm going to put together all my scalars, put all the alternating symbols together, and put all the other scalars together, and put the diode together. So I have alpha, alternating symbol I alpha L, alternating symbol JAB, alternating symbol beta CD. Then I have U alpha, SAC, SBD. Then I have EI, EL, E beta, EJ. Are we good up to this point? So that I don't get no's at a later point when we've gone far. Okay, Godwin, I see you. Fantastic. Fisayo, I see you. Mubarak, okay. Mujirade, fantastic. Now you will see that one of the examples we dealt with today, when you are composing series of diodes, you remember that we said you will take the first basis of the first diode, or the first vector of the first diode, take the last vector of the second diode, compose it together as a diode, then the inner ones will be a dot product. So we are going to apply that here now. So just focus on the diode now. This becomes EI, EJ, then the inner ones become a dot product. And when you do the dot product of your orthonormal basis, the dot product of your orthonormal basis gives you the chronicle delta. So EL dot E beta gives you chronicle delta L beta. That comes from chapter 1. I hope you don't mind me asking you, are you clear at every step? The reason is because I don't want to move too far before I now have to start coming over again. So are we good here now? What I've done on the diets? Hello? Okay, good. Of course, you see that these steps are not shown in the solutions. Now, the next thing is that your chronicle delta is also a substitution symbol. You will see that this has beta and this has beta. So I'm going to use the substitution symbol characteristics of my chronicle delta and swap those indices. L now goes to where beta is on the alternating symbol and the chronicle delta goes off. If I do that, then this becomes alpha EI alpha L, alternating symbol JAB. So instead of me having beta here now, it becomes LCD U alpha. Let me remove this arrow so that don't confuse you. SAC SBD EI EG. And the chronicle delta symbols goes off. Now you are going to use if you look at your chapter 1, you will see that I have L here and I have L here. So I'm going to use the characteristics of you writing your alternating symbols in terms of your chronicle delta. So I'm going to bring those two out. Just keep this for now. We are going to do another manipulation on the alternating symbols. Of course, you know that EI alpha L is the same as writing ELI alpha without changing the symbol. Am I correct? EI alpha L is the same as ELI alpha. Going in the anti-clockwise direction, you are not going to change the sign of your alternating symbol. Am I correct? What I said now, is it correct? Okay, good. Now, what we now want to do now is I'm going to bring out those two alternating symbols that have similar index on them. So I'm going to bring out ELI alpha, ELCD. From your chapter 1, you know that this you can write as chronicle delta IC, chronicle delta alpha D minus chronicle delta ID, chronicle delta alpha C. What I've written now, is it correct? What I've written now, is it correct? What I did right now is from my knowledge of chapter 1. Okay, Godwin said yes. Mubarak said yes. I'm not seeing Mujirade's chats again. Visayo, Bolaji, Damilola. I want to see you also to be sure that okay, Mujirade, this is step 1. This is step 2. And this is step 3. I'm now on 4. Which one is not clear? The last step. What I did in the last step, I brought this one out. I brought this one out. And from my knowledge of chapter 1, you can write that product in terms of conical delta. Can you remember that from chapter 1? If you can't remember that from chapter 1, all you just need to do is a pattern recognition. Is it clear now? Mojirade, is it clear now? So you can see that your first indices on your alternating symbol are the same. In conical delta, second one, the first conical delta, third one, okay, it's clear, fine. So from the fourth step now, instead of me having that E, I, alpha, L, and E, J, A, B, I'm going to replace it with the conical delta. So my fifth step, you have to have everything off hand though. That's why your self-test is just testing that you can recognize these patterns. And that is why all your tests is based on the examples. You see, we are not really giving you new questions, so to say. And you recognize it by practice, Bolaji. By the time you keep applying those patterns over and over and over again, you will see that it becomes part of you. I also had to go through that process. The last time I looked at these notes, I think was 2021, thereabout, 21 into 22 because of the strike. So all I just needed to do, I didn't need to keep it in my brain. So all I just needed to do, once I went back to the note, because it's stored away somewhere in the subconscious, I can recall it. The ones I can't remember, I just look at the patterns and I recall it. So Bolaji, you have to, because when we get to continuum mechanics, this is the language we are going to be using. So I hope it's clear to you. And it's not really offhand. You know why? Because the self-test is open book. The self-test is open book. So if you forget any principle at any time, even though it's timed, the ones that you find difficult to remember, just go to it. And if you have a note that you have written out these patterns, you can just have it with you when you are doing the test. I hope I've been able to give you some little hints on how to deal with this, okay? So my fifth step now is just to put this step 4 inside step 3. So I now have alpha, E, J, A, B, conical delta IC, conical delta alpha D, minus conical delta ID, conical delta alpha C, U alpha, SAC, SBD, EI, EG. So that's just it. So that's step 5. I have to move to step 6 now. Can I take off what is on the whiteboard? Can I take up what is on the whiteboard? Fortunately, we have some other recorded answered questions. Okay, Godwin said I should wait. So just go to the recording for PG 2021 videos. You will see some other questions I answered there. Okay. Can I go on? Time is ticking. We just have about 15 minutes. Okay, good. So step 6 now. Let me rewrite step 5 since I've taken it off. So I can link it to step 6. So in my step 5, I have half alternating symbol JAB into chronicle delta IC, chronicle delta alpha D. No. Is it alpha D? Yes, it's alpha D. Minus chronicle delta ID, chronicle delta alpha C, U alpha, SAC, SBD, EI, EI, EG. So step 6, half. Remember that your chronicle deltas are scalars. So it means that I can write this way. Chronicle delta IC, chronicle delta alpha D, SAC, SBD. If those chronicle deltas act on those the components of those tensors, and I open the brackets, minus chronicle delta ID, chronicle delta alpha C, SAC, SBD, U alpha, EI, EG. Take a look at step 6. Is it clear? So what I did was like I opened up the chronicle delta while it's multiplying the component SAC, SBD. That's what I did. I didn't want to miss that step because I'm going to do the substitution symbol of the chronicle delta. So I wanted to write this step first before we do that. So step 6, is it good? Step 6. Okay, good. So now let's use the substitution characteristics of the chronicle delta to write step 7. So this becomes SAI, the chronicle delta IC disappears. SB alpha, the chronicle delta alpha D disappears because I've used the substitution symbol quality or characteristics of that chronicle delta, minus SA alpha, the chronicle delta alpha C goes off, SBI, the chronicle delta alpha C ID goes off, U alpha EI EJ. So I just use that substitution symbol. Step 7, are we good? Good, good. Now let's look at what is in the brackets. If I swap alpha with I on this one, if I swap I and alpha, what happens there is that the sign here is like I've written, let me write it out. SA alpha, SBI is the same as negative SAI, SB alpha. Once I move the index from one to the other, what I've done is that I've altered the sign. Looking at this pattern, it means that I can rewrite this as this, so that the first term and the second term will be similar. That's what I want to achieve. And that gives me my step 8. My step 8 becomes half AB SAISB alpha minus SAISB alpha, and that gives us 2 SAISB alpha U alpha EI EJ. And remember, we have a half there. So this gives us SAI SB alpha U alpha EI EJ. Everything that we have done is to write U cross SC transpose in component form. That's what we've done. So everybody, please look at step 7 and step 8. If you are good, what we've written now is the right-hand side. So we are now going to write the left-hand side and check if we get the same thing. Remember that the indices used on the left-hand side was different. So all you just need to do is to check the pattern. Look at where A is here. Look at where A is here. Look at where your B is. Look at where your alphas are. Look at where your I is, and look at where your J is. So that's the right-hand side. Should I move on? Because we have 9 minutes and I want us to finish this question before we end the class. Can I move on? So this for the right-hand side. Okay, so let's go to the left-hand side. So for the left-hand side, I have ST composed with the SU cross. So you writing everything together. My S transpose, I wrote as SI beta E beta EI. And my SU cross is alternating symbol L alpha K, S alpha J, UJ, EL, EK. The last page, Godwin, you might have to wait to get the recording, because what it means is I have to be backtracking, and because the minutes are going. So Godwin, I just want to apologize. I guess you have to wait for the recording to complete that. But the last step, because I will need you to compare with this left-hand side, I'm going to write it. I'm going to write the last answer that we got so that we can compare what we have here. So I'm dealing with the left-hand side now. This now gives me alternating symbol L alpha K, SI beta, S alpha J, UJ, then I have E beta EI, EL, EK. Of course, you know that this will become E beta EK. The inner basis vectors become your chronicle delta because they are autonomous bases. And of course, as a result of that, I can do a swap on my alternating symbol with that L. So this becomes EI alpha K. The reason is because what I did was I did the substitution on the alternating symbol. because there's L there. So the L becomes I, and the chronicle delta goes off. SI beta, S alpha J, UJ, E beta, EK. So this is what I get for the left-hand side. Now this is left-hand side. Let me write what I got for the right-hand side. Then you can compare and see that they are the same. So what I got for the right-hand side was E, J, A, B, S, A, I, S, B, alpha, U, alpha, E, I, E, J. Compare these two. Can we see that it's the same? So compare what we got for the left-hand side. I've rewritten again what we got for the right-hand side. Can we see that it's the same? Good. All you just need to do, just check the placement of those indices and where they appear, and you'll see that it's the same. Okay, it's not. I'm looking at my, let me see whether I made a mistake on my E beta EK. Oh, I made a mistake somewhere. Just hold on for me. E beta EK EI alpha K SI beta S alpha J UJ E beta EK. You will see that this left-hand side, no, the only thing you need to do, the only thing you need to do, Godwin, this left-hand side, you know that I can rewrite it as E K I alpha. That's all you need to do. You just manipulate it. You just moving around it. You know the alternating symbol, EI alpha K and EKI alpha are the same thing. So if you rewrite it, you will see that it's the same. Well, Kenneth, I think you can. I just like to ensure that I'm not breaking any rules and making errors. So it's just a personal thing that I do. So if you can be very careful enough to track, it's good, because you know they are not together. The left-hand side and the right-hand side are not together. You are doing one part and you are comparing with another part. So if you are careful enough to track, no problem. But personally, I don't. All I just need to do is to check the placements. Once I can see that the placements are the same, then I'm good. Godwin, can you see that it's the same now? Godwin? So all you just needed to do was just rewrite that alternating symbol. That's all. In fact, and those are the trick things that you see in the self-test. In the self-test, they can write it this way, and you will think that it's not correct. And all you just need to do is just use your tensor vector manipulations to see if you write it in the other form, it will mean the same thing, and you will see that the answers are the same. Okay, Kenneth, I hope I was able to answer your question. And everybody, so all that we've done today, please go check the 2021 recorded videos for some other tutorial questions that I did not handle here. That will help you solve some other questions. The self-test instruction, admin, is it already on the website?
No, it's not on the website.
Okay, so please help me put it there. I will also send one to the course rep. It's going to, it should be open. I thought it was supposed to open at 9 a.m. today. So I thought it would be on the website. But anyway, it opens today and it closes next week, Tuesday, 11:59 p.m. So 1 week. Don't attempt the self-test without you being ready. The most important thing is that you do it before the deadline. and you are in a good place with a good internet connection, but there is no rush. I could see from self-test 1, I feel that the results, like somebody actually got the whole question correct. And I feel one of the reasons is preparation. Like one of the things Bolaji asked me today, how do you remember this pattern? You can have a place where you jotted, looking at the patterns and all that. It's an open book test. Nobody's with you. You are not being supervised. So if you now want to get the lazy way out, you don't go through the recordings, you don't go through the materials well, and you now go and say, let me just attempt. It's a multiple choice, and you feel that you can just by just doing some manipulations, you do well. This doesn't work that way. You must actually understand what you are doing. So it closes next week, Tuesday, 11:59 p.m. Don't attempt it until you are ready, but ensure you do it before it closes. Okay? Thank you, everybody, for coming. Check your schedule again. The next time that we'll have this kind of session is the tutorial session for chapter 3. Okay? Any questions before we leave? Maybe 1 or 2 minutes before we close the meeting. Okay, I think we are good. So I will send the instruction to you today, but just for now, it's next week Tuesday, 11:59 p.m. Next week Tuesday, 11:59 p.m. But I'll send the PDF of the self-test instruction to your course rep now, and to also be posted on the website. Okay, bye-bye everybody, and all the best in your self-tests too. Okay, admin, I think we can close the meeting.